Welcome back. Uh, so the plan for today is finishing the cache coherency part and then start talking about consistency. And then I'm going to also give you an overview of the remaining things that we need to discuss in this class as well. So if you remember, we were talking about the coherency problem. And we said that the coherency problem is when we have multiple copies of the same address in different caches, right? So, and then we said that why we need different private caches for performance purposes and why there's no an easy solution for this problem. We also motivated the need for thread level parallelism and why we need to have multi-threaded parallel programs. Um, and then we also said that there are a bunch of other performance reasons and things to consider that for the sake of time and scope of this class, we're not going to go through them. But we're going to talk about, as we said, about two important problems: the coherency and the consistency problem. And again, this was the motivation of why we need private caches versus shared caches. Um, and then for the coherency problem, we essentially define what we need from the coherency. And we also talked about other alternatives, such as using software or using hardware. We eventually decided to do this thing called snooping-based cache coherency protocol, which the idea was that you snoop all the actions in all the caches from all the cores and make some decisions based on that. Essentially, every line has a coherency state. And then we started with like this MI, which is like the simplest one. And then we add the S to it and created MSI. We said that essentially every line in the cache in every single core will have a bit or sequence of bits, depending on how many states do we have, and maintain that state. And depending on the other activities of the other cores, it will update that state. So initially everything might be I and then become an S or an M and so on and so forth. And this way we will ensure that everybody has the right copy, or if they don't have the right copy, at least they invalidate themselves so they don't maintain any copy in their cache, an incoherent copy in the cache. We talked about the MI and MSI, and then we said that essentially the idea in cache coherency protocol is balancing the performance and the other overheads, including the area overhead for storing these coherency states, as well as the complexity of the algorithm itself. But what we are really trying to do is making sure that the overall performance of the cache system is high, which means that we want to, again, maximize our hit rate, right? You want to maximize our hit rate, you want to reduce your miss rate, you want to reduce your miss penalty. That's the ultimate goal in memory subsystem, and cache coherency is no different. You want to still maintain those things, okay? So that was kind of like the last thing that we talked about in terms of coherency. We talked about an example of an MSI. And then we also talked about the dirty lines and walk right through versus right back and the dirty bits. So when we are actually invalidating a dirty line, we need to write it back to the memory, and the new line should be read from the memory in order to make sure that the values are updated. Okay? So any questions so far from the MSI, or should we move on to the optimizations of this? Yes. The MSI protocol? Yeah, sure. So for example, let's say that we have a sequence, like we can redo this. We have a sequence like this. As I said before, these are all same addresses. So coherency is for the same address. It's not for different addresses. Different addresses, they just do differently. You don't need to be worried about them. So these are all for the same addresses. The terminology syntax I'm using here is when I say like R1, I mean read from core 1 to that address. So let's say that address is Z or X or whatever number it is. So all of these red ones are from the same address. So first core number 1 read that address, then core number 2 writes to that address, then core number 3 read from that address, then core number 1 reads from that address. That's kind of like the sequence that we're going after. Yeah. Yeah, each core has its own private cache, right? So there is a shared layer of cache, and then there's a private cache, okay? So, and then here I'm just assuming I have 3 cores, but then this could be extended to any number of cores, right? It doesn't matter. So initially, when those lines are not cached in the private cache, obviously all of them are invalidated, right? So they're not stored in the cache, so their state is an invalid state, okay? Then once the first request comes, that is this read number from the core number 1, then core number 1 wants to cache this value inside their private cache. So what they do is that they read it from the main memory, they bring it to their private cache, and they switch from the I state to the S state. S means that it's possibly shared, not necessarily shared, but possibly shared, and it's only read. So it's, we haven't modified the value yet. Okay. So what happens is that initially we start from all I states. Then in the second cycle, core number 1 for that particular line transition from the I state to the S state. So it essentially like would be something like this. If this is core number 1, this is core number 3, this is core number 3, this will happen. Okay. Everybody else stays in their own I state. There's no reason for them to update, right? Yes. So the core 1 read it from the main memory because nobody has the copies yet. And then put it in its cache. Put it in the cache, yeah. Think about the classical cache miss scenario that we learned in the past. And so yeah, so it's broadcast, right? So the way all of these things happen is that it's broadcasted, so everybody will listen. And if somebody has that value, will written back to the memory and all that. But since nobody answered to this broadcast, it knows that nobody has the copy, so it goes to the S state. Okay? So that's the story of this second cycle, okay? So this is for this guy. Now the second thing happened, and that is that at some point later, not necessarily the next cycle, it could be hundreds or thousands of cycles, core number 2 will try to write to that address. So this is a store instruction. So it tries to write to that address. What will happen is then when it's trying to write, it will again broadcast it to the entire cache. Core number 1 will see that someone is trying to write to this address that I'm caching, which means that now I need to invalidate myself because the copy that I have is no longer the correct copy because someone is trying to update this line, right? So I don't no longer need this line. So I'll invalidate myself. That's why you see that this basically, I'll transition back to the invalidate for core number 1. At the same time, core number 2 is trying to update this value, right? So we'll transition from the I state to the M state. So you will see that there's also like this I to M happens. And core number 3, again, has nothing to do with any of this, so it's continue to staying in the I state, okay? So that will be kind of like what will happen for this cycle. Then we go to the next one, and what will happen here is that core number 3 now wants to read it, okay? So again, it will broadcast this value. The difference in this case is now core number 2 has this line in the M state. So it means that the copy in the core number 2 is the most updated copy. The copy in the memory is a stale copy, is the wrong copy because it hasn't been updated yet by core number 2. So imagine that we are doing write back. If it did write true, then both copy in the main memory and core number 2 are both updated. But if you do write back, only the copy inside the private cache of core number 2 is the most recent and updated value. So what will happen is that once R3 is broadcasted, then core number 2 will intervene. And what it does is that it tells the main memory, don't forward the value yet. I have the modified value. Let me update the content of the memory first, then you forward the value. So there will be a write back happening here, which we usually show with a star, for example. This is just an arbitrary syntax. So we write back, then we move to the S state, okay? Because now I have the clean copy, and then core number 3 can transition from the I state to the S state as well, and the read happens from the main memory. Okay, so the read happens from after core number 2 update the main memory. The core number 3 will read it from the main memory. Okay, so what will happen is that at this stage you will see that core number 2 is in the S state, core number 3 is also in the S state, and again, core number 1 is already invalidated, stays in the invalid state. Yes? Yes, so once the read is broadcasted, core number 2 will write back, then core number 3 will read. So the sequence is like that. So it's kind of like happens in between the transition between M to S. And then lastly, if R1 also wants to read, since everybody has shared a clean copy, one will read it from the memory, everybody else stays in their S state. So at the end of this sequence, everybody's in the S, everybody has a clean copy, and then after that, they will continue to stay in S unless either they will be kicked out by another cache line. So it's still, one of them might be transitioned from S to I just because there is a cache contention, there is a conflict misses. Or if someone tries to write and goes to the M, everybody else will invalidate, right? So for example, here, what could happen is that if there is, let's say, write 3, what will happen is that both core number 1 and core number 2 will transition to the I state because no longer they should maintain the copy, and core number 3 should go to the M state. Okay, so that's how this process happens. Yeah.
Why is it when in W2, like when it writes, so it doesn't even touch base. What you're saying in the aspect there, it first writes to the cache, its own little cache. It writes over the value that it doesn't do anything.
You mean here?
Yeah.
So here no write happens, right? So here, if W2 tries to write, if it's a write back strategy, it's only writes it to its own private cache and not to the main memory. If it's a write through, then no, it writes both to the cache and to the main memory. So it depends. Okay, this is the state machine in case you're interested. So let's talk about these other 3 states, E, F, and O. The key idea here is that we want to further optimize this MSI protocol. Many of the conventional machines just use MSI. They don't go further than that. But also many modern machines use some combinations. So some of them are messy or mosey or messif, and so on and so forth. All right, so let's see why we need these states. Let's start with E. So the E state is needed to create some sort of what we call a silent upgrade. So what is the idea? The idea is that let's say I have a core in S, okay? And that core wants to write to its own data. So I only have one core that has the valid copy, and the same core wants to write to that value. So have something like this, R1 and then followed by write 1. Currently with the MSI, whenever we have write, okay, we have to broadcast it to everyone else because we don't know whether or not others have the copy of that or not. If I'm in S, I have no idea if the other cores are also in S or they are in I. There is no way of distinguishing this, okay? So if this core wants to go to the M, it has to broadcast and tell everyone that I'm writing. So if you are in S, you have to invalidate, right? But if I'm only one, I have the exclusive access to this line, then the broadcast is unnecessary, right? Because I'm the only one who has the copy. Nobody needs to know that I want to write. So I can save on the broadcast if this line is not shared with the others, okay? So that's the motivation behind having another state called E. E is same as S. The only difference between E and S is that if this is an exclusive copy, it means that it's not really shared. We transition from I to E. So generally, here's the idea that if all of them are in I and someone wants to read, for example, R1, instead of transitioning from I to S, we transition from I to E because right now it's exclusive, okay? Then if someone else wants to read it, then we will transition from E to S because no, it's no longer exclusive, right? The benefit of this is that it removes the unnecessary broadcast when it's exclusive. And why does that matter? Because many lines are actually exclusive. There are many lines in your program that are in fact exclusive because only a few lines that are indeed shared between cores. Only a few memory addresses are indeed shared. Most of my addresses belongs to one process and one process only. They're not shared and they can stay in that one cache. And if we don't have the E states, essentially for every write to my own address space, I'm just creating some unnecessary broadcast to the rest of the cores, which is very time consuming and energy consuming. So you want to minimize those unnecessary broadcasts. If I'm writing to my own addresses, nobody needs to know, right? So that's the motivation behind the E state, okay? So essentially, this will introduce what we call a messy protocol, which we have the M and S and I and E on top of that, okay? So what will happen is that, as I said, on a read miss, that if everyone is in the I state, the line that requesting that address transition from I to E, okay? If one line is in E and another line wants to also read that line that is in E goes to S, and the other line also goes to S. This is just a regular S shared core. And then if the key thing is that if someone is in E and wants to write, it goes to M, but it doesn't need to announce it to everyone else. Okay, so it's just silently go to M without broadcasting it to everyone else. Okay, and everybody else already in I, so you don't need to do anything. Yes.
But in terms of previously, if any like core needs to modify something, it goes to the next stage.
Yeah.
All other cores in another stage.
Yes.
In this case, we don't have exactly the same result.
Yes.
The only difference is that we don't need the modify.
Yes, the only difference between MESI and regular MSI or S and E in particular is that transitioning from S to M require a broadcast, but transition from E to M doesn't require a broadcast. Okay? Yes.
Then another word can take it. And with the first core being a state, the core being this.
The second core being on what state?
The core that got the first that be and
so if one is in E state, everybody else has to be in I state. It's not possible to be in another state. So if someone wants to request it, that one goes to S or M, and then this one goes to S or I. Mm-hmm. Yeah.
Question, exclusive just means that that actual address isn't even in the other.
Yeah, it's not shared. It's not even shared with any other cache, which is actually the majority of lines in the memory. That's why having E is really important. Okay, I'm going to skip the example because I have another one with that example. So I'm going to actually do a big example with all of them. Okay. All right. So that's one problem that we solved. So we reduce the unnecessary broadcast, especially for lines that are not shared. But here's another problem. So let's say that there is a core that is already in M, okay, and others are in I, right? And we said that if someone wants to read this value, the way it works is that that value needs to be written back to the memory. Then the other code reads it from the memory, right? And this is very, very inefficient in terms of timeline, right? Because this needs to go to the main memory. This one has to come back from the main memory. But why don't we just forward it from the one that has the copy to the other one? That would be a cache-to-cache transfer, very quick. Instead of going all the way that we need to have a write to the memory and then we need to read it from the memory. So that's very slow. But how do we actually do that? Um, uh, we use this thing called the owner states or O state, okay? And owner states basically distinguish between who originally wrote to this line in the memory versus who takes the copy of that memory, okay? So the way it works is that if you have something like MOSI, so same as MSI, but now we introduce O. So right now we don't have E, we just have MSI and now O. Later on, we're going to have MOESI. But for now, let's say I'm just introducing the O. So what will happen is that if I have MOESI, I have everything similar to MSI with this only difference that if someone is an M and another core wants to read, the one in M goes to O instead of going to writing back to the memory and going to S. It goes to O and it provides the data. Okay, so there is no need for write back. Okay, and there's no need for a memory read. It's a cache to cache transfer. Okay, but then if one core is in O and the other core wants to write, then that's when that M will invalidate itself. Usually this follows by a write back. So O writes it back to the memory and then the other one is happening. The reason for this is usually that we want to have the latest copy in the memory anyway, so we don't want to lose any data in between. But in some rare cases, you can also even skip the write because the other one will replace that write. But typically, the way it works is that if someone wants to read, the O will provide that data. If multiple cores wants to read, O continue to provide that data. Okay, so keep that in mind. Yes. It's a dirty forwarding. So it forwards the data, but it forwards the dirty data. Okay? Because later on, we're going to have a forwarder state, an F, that is actually forwarding the clean data. So there's a difference between dirty, like an O and an F. Yeah.
Like in O state, how would you really write that?
Yeah. So let's say, for example, I have core number 1, 2, and 3, and this one is in O, this one is in S, and let's say this one is in I. Okay. And now let's say core number 3 wants to write. So I have something like W3. So what will happen is that this one goes to I, this one also goes to I, and this one goes to M. But at this point, there's also a write back happens at this stage.
I see. But the M here does not write that.
The M does not write back. Yeah. And then if, for example, let's say this continues. So let's say now I have something like read 2. What will happen is that this stays in I, this one goes to S, but this one goes to O. Okay? And the important thing is that the data is kind of provided this way. So the data is provided from M to S.
So when O changes to I or other states,
yeah. When someone else wants to write and you have to invalidate, then you write back. Yeah. So if I have something like this instead, you're saying that if I have something like W3 again, is that your question?
To the second floor,
So it's like write one.
Yeah.
Yeah, if it's write one, then you again transfer to M, and then these guys will be I. Oh, do you write back? You mean like do we do the write back here? Is that your question? Is that a question or something else? Yeah. So if, for example, one is already in O and it wants to update its value, then of course it has to go to M. Everybody else has to invalidate because the copy is no longer valid. Yet we usually, as I said, we typically assume that this happens. That is like we do a write back. But I can give you like we usually define the exact algorithms when we want to ask that. There is like there is the write back from back to back writes is usually like implemented differently in different setups. Technically, you may not need to write this back because essentially you're just updating the value. Yeah.
You didn't have the O state, then if you wanted to invalidate,
Uh-huh.
write back to main memory, depending on either if you use write back or write.
Yes, if it's write through, then of course there is no write back necessary. So all of these discussion on the write back is only for write back strategy. If it's a write through strategy, then you're good to go. Mm-hmm.
Right, right. When you with like the affix, is that right? That kind of thing on L or is that kind of on I?
You mean this scenario like this, right?
Yeah.
So you're asking when does that write back happens?
Yeah.
Yeah. So again, so the question is, if this one is going to write, why do I need to write back to the main memory? As I said, typically this is just to make sure that if there are other accesses in between that we haven't scheduled yet, because there's also the out of order scheduling that might happen. This will just ensure that that happens. But as I said, this is possible that you don't need to write back. So that's also an option. So again, that's really implementation details of like with the memory model and what is possible. But technically you may not need to do this write back. Uh, so the question is, do we put the write back here or here? That's really just a syntax. So the reality in hardware, what will happen is that before this transition, the write back should happen. So it's kind of in between. In the homework and quizzes, we have a specific model. We say that, okay, put it in here or there. You just put it there. But it's like, this is just that's the syntax. It's not like a specific rule. I think we put it here usually, but I'm not too sure. We just have to check this solution, like a homework. We'll define it where to put it. Okay. All right. So as I said, we can have both O and E, MOESI. So you can get the benefit of an O and an E at the same time. So E gives you the exclusiveness, and O gives you the ownership and the forwarding of dirty data. Lastly, you can have the F state. The reason that you want to have an F state is the following. Imagine that you have multiple cores in S, okay? And now a new core wants to read. Who provides the data? Without a forwarding, there are two options. Either the new core, so let's say, for example, core number 2, 3, and 1, 2, and 3. So this one is in S, this one is in S, and this one is in I. And now core number 3 wants to read R3, okay? So the question is, who provides the data? Option number 1 is that core number 3 go and grab it from the main memory. That's what we said so far. In the MSI, that's what we do. Core number 3, even though that 1 and 2 has the data, they don't provide the data because they don't know which one should provide the data. So 3 and go and read it from the main memory. That's very slow. The other option would be some form of a round robin or like whoever, like a first come first serve base. That V3 will broadcast it at one data. Whoever can provide it the soonest provided. So that could be also an option. To formalize this, we usually have a forwarding state in order to make sure which one is providing the data. This is to ensure that there has some form of a fairness, and we ensure that the traffic is actually distributed equally. Okay, so the way it works is that we have from the one that is exclusive, from S it goes to F instead of going to S. Okay, so typically F comes with an E, because in order to be a forwarder, you need to know that which one was exclusive so that that one becomes a forwarder. Okay, so usually that's what happens. So for example, let's say I started from I's. Let's say core number 1 reads, and then this one goes to E, and the others stay in I. And now if core number 2 tries to read, E goes to F, I goes to S, and this one goes to I. And what will happen is that here the data is provided by by core number 1. So this is a cache-to-cache transfer rather than 2 going to the main memory and read it. And again, this continues. So if R3 tries to read, again, it will be a forwarding from, again, core number 1 to core number 3. Okay, so this is forwarding logic, happens all the time. Whoever has the data initially, that's the one who forwards the data. Okay? All right, so yes. You can have O here as well. O is for the dirty, right? So O is from M. So from M you go to O. From I you don't go to O. So actually here's the transition. So the transitions are like this way. So from I you go to E if you're the first one, the exclusive one. And from E, if someone else wants to read it, you go to F. Okay? If you're in I and you want to write, you go to M, and everybody else go to I. If someone else wants to read, you go to O, because now you are the owner, but there is a copy, like you want to also forward your dirty copy to other people as well. Okay? And then if you're in E, you can also go to M, but the M that you go to will be a silent one, so you don't broadcast. So the difference between S to M versus E to M is the difference between silence. Yes?
I'm not understanding why the growth state doesn't lead to race conditions.
Why O state need what?
Doesn't lead to race conditions. Doesn't mean growth state is dirty or
How? So you're saying what O is not a race condition? So so everything is broadcasted, right? So when you want to read something, so for example, if someone is in O and someone else is in I and wants to read something, it will broadcast it. Okay? And the broadcasting happens with a controller. So the controller decides who does what. So in this case, O is the one that's providing the data, not the memory. Are you asking that between O and M there is a race condition? Is that your question?
what is the point of the M state if the growth state is sufficient?
What is the point of M state if O state is what?
Is sufficient to do it without that's sufficient to do it not to be data without this.
Oh, so you're saying that like from I just go to O and not to M? From M, so the reason that you want to be, so M gives you the exclusiveness versus O is a shared. So the difference between M and O is that if someone is in M, it's exclusive. If someone is in O, it's not exclusive. It's shared with the other cores. That's the main difference. Okay? You other question?
Oh, yeah, I was gonna say, so it goes to E.
Uh-huh.
What E when you read, okay? And then you go to M, right?
Yes. E is for read and M for write. Yes.
Sorry, maybe the question F and O. So I feel like they both have the one that's shared.
Yeah. O has a dirty copy, so O only happens from transitioning from M, but F happens only from the E, so it's a clean copy.
But in E and M, they both only one with the
Yes. So you're suggesting from M I go to F, for example.
Yeah.
Yeah, but so the only difference is that now I need to know whether or not I should write back. So F doesn't write back, O does write back. So that's the key thing. Yeah.
Does that only apply for posted?
F could be like, MO. It could be like, could be this as well.
Oh, but there's no F in it, if there's no F in like the term.
Yeah. Yeah. So this terminology, when you see this, it means that which states you have. So if you see something like this, it means that you only have M, E, and S and I. Yeah. Or you can have like MOSI or MOESI and so on and so forth. Well, we only covered 6. There are a few others. Some of them, as I said, these are just optimizations, so they're not necessary. But some of them are somewhat redundant. But yeah, we only cover these 6. So that's usually the common ones. Yeah.
For MO side, where do you also need the conversation mentioned earlier? Should we be
You usually pair F and E together. But if you don't have E, then you go like a round robin. So you can just randomly assign one of the S's to F and that's it, right? So you don't necessarily need an E to have an F. But that's typical because it makes the implementation easy. Otherwise, it's like an arbitration. So you have multiple S's, one of them has to become F. Any other questions? Yes. Uh-huh. 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 So we always do one request at a time, right? So that's why you can share it to both. So the question is, can I kind of forward one thing to multiple cores at the same time? That would be kind of like a broadcast type of activity but typically in the memory, things will be serialized, right? So it will be first access, second access, third access. But yeah, if your memory bus supports broadcasting, then you can forward to all of them at the same time. In fact, that's actually very efficient in some cases. So imagine, for example, you want to read a partial sum, and you just update everyone's partial sum this way. Any other questions? Okay. So you're gonna see examples in the homework. You're gonna see examples in the discussion sections. You're going to see examples in previous homeworks and all. Make sure that you practice, you understand the difference between these states. It's fairly straightforward. And again, make sure that you understand the necessity of why we're having these different states, right? So essentially, if I want to summarize the need for these different states is that it's remove the unnecessary broadcast. It removes the extra write backs to the memory. It removes the memory accesses and gives you cache to cache transfers. So these are the kind of key things that these different states will give you. Okay. Any final question about these states? Yeah.
So the extra right backs is fixed by F.
Extra write backs fixed by O. F is clean.
Yes, I thought F doesn't. Oh, yeah.
F fixed the issue of not going to the main memory for reads. Okay. So there are other quick things I want to share with you for coherency, and then we move on to consistency. There is this thing called false sharing. False sharing is that when we have multiple lines per block, remember I told you that we have blocks in the cache that has address 1, address 2, address 3, address 4, and so on. Typically, we store things at the block level for coherency. So if I have, let's say, a block of 8 bytes, for all the 8 bytes, I store one metadata. But what that means is that if one of the lines is shared and the other one is not shared, everybody will be kind of on the same boat. And that is, if I invalidate a block, all the lines within that block will be invalidated. But it might be that only one of those lines are in fact shared, the others are not shared. Okay? This is called false sharing because we address things at the line level, but we maintain the coherency at the block level. And for example, if 2 needs to be invalidated, unfortunately, we also invalidate 1 and 3 and 4 and 5 and 6 and 7. In fact, they don't need to be invalidated, right? But since we do everything in the block-based granularity in cache, then we invalidate everything at the same time. This is the notion of false sharing because 1 is not shared, but it's kind of like, whatever 2 is doing, 1 has to follow as well. So just keep that in mind. And then as a result of this false sharing, we might have extra misses because essentially if I have a line that is being invalidated and then the other line that weren't supposed to be evicted from the cache and now it's a miss, that would be what we call a coherency miss. Yes. No, so here I mean like an address. So like address 1, address 2, address 3, address 4. That's what I mean by a cache line. So what will happen, as I said, is that for example, you need to invalidate address 200. But since this is a block, you also invalidate 201 and 202 and maybe more, depending on the size of the cache block. So later on, when you're actually accessing 202, it will be a miss, and we call this a coherence miss, because 202 was invalidated as a result of 200 being invalidated. So you see the difference. If 200 is invalidated and it's a miss, it's a regular miss. But if it's 202 is invalidated because of 200 and it's a miss, that's a coherent miss that we also need to take care of. Like we need to be aware of this. Okay? Yes.
Very good. But like the analysis is for all the questions. When you're sort of choosing a block, but it's no process at all.
So what it says is that if I have a block of multiple addresses, right? I usually maintain a coherent state here. So if I decide to invalidate, I'll invalidate all of these guys. Okay? But what happened is that if I only needed, so if I had just 1 bit per, like a coherence bit per block, per line, per address, then I could have invalidated each one individually. So the others would have stayed in the cache, well, versus the other ones would be invalidated. So this is kind of like the trade-off. If I do things at the block level granularity, I kind of do a little bit of a coarse grain tracking of the coherency. And that will result in extra misses that may not be necessary. Does that make sense? Cache line here means that each address, each byte. Okay, so maybe I'm using the right. So ignore this. Just listen to what I'm saying. So you have a block, okay, and then you have a coherency state here. You have different addresses here, okay. If I'm invalidating, I'm going to invalidate them all, which I shouldn't, because if, for example, I only needed to invalidate this one, but now I also invalidate this one and invalidate this one. Does that make sense? I'll fix the text in this. As I said, this is what we call a snooping behavior and a snooping protocol. this is just one way of maintaining coherence. There's also another way of maintaining coherence, and that is directory based. So snooping is okay for smaller systems that you can snoop a lot of things at the same time. But if I have like 64 cores or 128 cores, then snooping becomes very, very complicated because every core might have an access, everybody else has to listen. So it's not very scalable option because everybody has to listen to everything else, okay? So typically for large scale systems, we have what we call a directory-based coherence protocol. Directory based means that we maintain the mapping of the data inside the main memory. Okay. So essentially what we have is that we have our private caches and we have one main memory, right? And each address in main memory will have what we call a directory, okay? Which is essentially could be 4-bit. That 0 and 1s in this means that whether or not I have the copy here. So if it's all zeros, is equivalent of 4 i's. If it's like 100, it means that it's in the cache number 1, but it's not in cache number 2, but it's not in cache number 3, and so on and so forth. Now I can also do other things. If it's a dirty bit, for example, I can have another bit. If it needs to be written back, I can have another bits, and so on and so forth. Okay? The good thing about this is that I don't need to broadcast. Everything is done in the memory. The problem though is that now I need to have access to the main memory, right? So there's like this, for coherent space reading, I need to actually access the main memory. So there will be a little bit of challenge of implementing this in terms of the bandwidth to the main memory and also the latency that might apply. For very large systems, this would be beneficial because essentially all I need to do is just go to the main memory, read the directory, and that's it. No broadcast necessary. Okay? So it's much simpler for large scale systems, not very beneficial for small systems. Okay? I'm not gonna, there's a little bit of details into like, how exactly do you implement this? I'm not gonna go through it because of the time, but just keep in mind that there exists directory-based coherence protocol as well. It's actually quite common for very large scale systems. Okay? Perfect. All right, that's it for the coherence. Any final questions or should we move on? Okay. Let's have a quick, like 2 minute, 3 minute break, and then we're gonna talk about consistency. This is by the way, bonus for question for quiz 2. We will leave it open until your quiz 3. So there will be also an opportunity for bonus for submitting evaluation, course evaluation. I'll post it today on what to do. So please start submitting your course evaluations. Yeah, usually that's the number. In the course evaluation, we take the course evaluation very seriously. I always read them and see what works and what didn't work, and then we usually make adjustments to the next year's offering. So if anything that you want to change or things that you feel like didn't work out or things that you really like or any suggestions, recommendations, please put it on the course evaluation. I read them very carefully and then kind of make decisions for the next year offering based on those. Okay.
Recording in progress.
Yeah. So that's please take some time and do it. And then as I said, usually if you hit like 75% or 90%, there is a bonus point. So please participate. Okay. So consistency problem. Remember I told you that in addition to coherency problem, we have the second problem, which is consistency. Consistency coming from the fact that we have parallel programs, right? So we have multi-core, and having multi-core means that I can run and I can divide one program into multiple threads and run it on these different cores. And since they run in parallel, I can improve the performance of the system. So the end-to-end latency significantly shrinks if I can actually distribute the workload in multiple cores, okay? But the problem that I'm going to face is two problems. Is the synchronization problem and is the memory consistency problem, okay? So what is the problem, or what are these two problems? Is that if I have a code like this that is from the same program but multi-threaded, so it runs in core number 1 and runs in core number 2, same program, what will happen is that depending on the orderings of these instructions, I might have different values for my variables. So for example, in this case, x1 and x2 might get different values depending on which of these cores or which of these instructions goes first. Important things about multi-threading is that it's really hard to predict which core will be slower versus which core will be faster. So there is no synchronization among the cores. One core might be too fast, one core might be too slow. One core might have a cache miss or misprediction. The other core might not have a cache miss or misprediction. So the sequence of program, even if it's the exact same program, might be very different in terms of time, okay? So as a result, the values that I'm going to get here will be different. But then in addition to that, synchronization is not the only problem that we are facing. The second problem that we are facing is the hardware optimization or the compiler optimization. That within each core, if you remember when we were talking about optimization, we said that, oh, there is possibility of reordering instructions within one core as long as these instructions are not dependent to each other, right? So if they were dependent, you couldn't, but if they're not dependent, you can reorder them. Why you want to reorder them? In order to improve the performance, to reduce the stall cycles, right? So all of the speculation loads and load store forwarding and all those tricks that we talked about is applicable and still applicable. So additional problem that we're going to face in multi-threading program is that not just the synchronization problem among the cores, but the reordering of instructions within each core. So that's a very, very challenging problem that we need to face in the consistency, okay? So as I said, there are two class of issues and both of which needs to be fixed in order for a multi-thread program to work. The first is the race condition, that writing a parallel program is generally fundamentally different than single-threaded because of the timing. In order to fix this problem, this is, by the way, a programmer's job. So the programmer needs to understand the synchronization problem, this race conditions, and they need to use this, what we call synchronization primitives, in order to fix this problem. Some of you probably have heard about locks, mutex, fences, semaphores, and so on and so forth. These are different type of primitives that we use in order to synchronize the cores. And this is the job of the programmer. But on top of that, there's also the problem of reordering. So what is the role of hardware in all this? First of all, hardware provides support for synchronization, okay? So many of these synchronization, and we're going to talk about fences, we're going to talk about locks and barriers and so on. You're going to see that there are actually hardware or architecture-based support to do that. So literally in RISC-V architecture, ISA, there are instructions for fences, or there are instructions for atomic reads, or there are instructions for grabbing the locks or releasing the locks, okay? So that's one thing that we're going to cover in this lecture. The second thing that we're going to cover in this lecture is the beyond race condition, and that's what we call the consistency problem. For example, in this particular case, you can see that based on the out of order optimizations that we described earlier in this course, there might be a scenario that you get read 0, 0 for x1 and x2, and that is when basically what will happen is that these things are these things are happening before this. So actually, it would be not 0, 0, it would be 100 and 200, right? So if both of the stores happens before the loads, then what will happen is that you might get updated values that you're not anticipating. So this is not just a synchronization problem, but it's also reordering problem. And as I said, this is not a raw problem. This is not a correctness problem because these addresses are different addresses. So Y and X are not the same address. This is not something that will be caught by your processor itself. The reason that you have this problem is that this Z is same as this Z in another core, and these two don't talk to each other. So CPUs don't talk to each other. So like LSQs don't talk to each other. Okay? So that's why we have this problem. And then, as I said, for LSQs, this could happen. So we can like move the load before the stores and so on. Another thing that we didn't talk much is that the compiler can also reorder things. And then again, you might think that this is the order that you're going to see, but in fact, the compiler actually put the store before load. So this reordering could also happen at the compiler stage, just FYI, okay? So generally, consistency problem is the following, that stores and loads to different addresses within one core will be reordered and seen by other cores differently. So things are different from different vantage point in the design. And this will mess up the assumptions from the other core. So you can, like when you're writing your program, you cannot assume that this is not possible, okay? And again, one thing that I usually see is that people always confuse the difference between coherency and consistency, and they say that, oh, why the snooping processor, like the snooping strategy cannot fix this problem. The snooping strategy only works for the same address. We snoop the same address. So when we are broadcasting, everybody else look to see if they have the same address that's being broadcasted. Consistency problem is about different addresses. That is, I'm writing to Z, and then like reading from Y, and this other course is reading from Y or writing to Y and reading from Z, something like that. So so this is the problem that we are facing in the consistency versus in coherency is like reading to Y, writing to Y, reading to Y, writing to Y, or something like that. So it's all about the same address. So just be careful about the differences between consistency and coherency, okay? So how do we fix these problems? How do we fix the consistency problem? We fix it by, so as I said, there are two problems, right? The first problem is the timing or the race conditions, and the programmer will fix this. We're going to talk about this. We're going to fix it by inserting synchronization primitives like fences and locks and all that, okay? The reordering problem, we also need to fix this. And this is not the programmer's problem because programmer will not be able to see this reordering. So this needs to be actually fixed in the hardware, okay? How do we fix this problem of reordering? We fix this problem by having what we call a memory model, by knowing the memory model. So basically telling the programmer what is possible and what is not possible and enforcing this possibility, then the programmer will understand the memory model and write their program based on that memory model. So the complex things about this parallel programs is that what you write for one specific hardware is not applicable to another hardware. So it's not like your regular C or Python programs that you compile it on ARM and it works, and then you compile it on x86 and it works. And if they have different memory models, then this may not work because possibilities in an ARM core is very different than the possibilities in an Intel core. And same for RISC-V. So for example, RISC-V memory model is very different than x86 memory model. Okay? So we need to be able to know what are the possibilities, and that's what we call a memory model. We pass that knowledge to the programmer, then programmer put their synchronization primitives, and that will make sure that you only produce the very deterministic results in your program. That's how we fix the consistency problem, okay? So what are those memory models? There is the famous one called sequential consistency or sequential model. Sequential programming means that just the most intuitive way of writing a program, that all the loads and stores happen in program order. If I can do this in hardware, essentially throwing out all those optimizations that I said and pass it to the programmer, then the programmer can reason about this and write their programs correctly. Again, this does not fix the race condition, but basically what this says is that if you see in your program a store and later on you're going to see a load, sequential consistency memory model says that it is guaranteed that this happens before this. Okay? So programmers can reason about this way. So and that's a very important thing for sequential consistency. Okay? Essentially, what the sequential consistency does is that it makes it indistinguishable for just a multi-program in-order processor. So that if I have multiple cores, all of them in order, the same way that you read that program is the same way that you read a sequential consistency program. Okay? So no reordering is possible. What is the problem though? The problem is that essentially all of those cute tricks that we introduce of like, oh, if the address is not the same, let's speculate and let's issue it faster, or let's wake up early, and all those things to save cycles within the functional units, they're all gone, because essentially this enforces that you cannot issue a load before a store, or you cannot issue a store before a store, and so on and so forth. Okay? So sequential consistency is great, makes things very simple and reasonable and intuitive for a programmer, but most of the time sequential consistency is not what we are using in modern processors because of the stall cycle. So we want to have a trade-off. We want to push some of the difficulty to a programmer to be able to say that, okay, we want to actually be able to reorder some of the things, but now the programmer needs to work a little bit harder. Okay, so the trade-off is this. Any questions so far? Okay, so what are the orderings? So all the possible orderings is the following, right? So read and write. So for example, if we enforce the write read order, means that all the writes must complete before subsequent read. If we have that, we say that we enforce the write read. All the reads must be complete before subsequent read. This is the read read. Read write is that all the reads must complete before subsequent writes. Write write means that all the writes must be complete before subsequent write. Subsequent here is that the order of the program. So read read means that if I have some load word here, and then later on I have some load word here, if I enforce this second ordering, it means that I need to guarantee that this happens before this. Okay? And similar for the store word and so on. Sequential consistency basically enforces all of these things. Okay? So it says that no reordering is possible, read or write. Okay? And again, I want to emphasize this again, that these are for different addresses. It's not for the same address. So this is not a raw data hazard. Remember, in raw data hazard, we say that, for example, if you have read and write and then read after write needs to be followed. So if we do this read before this write from the same address, this leads to correctness issues, and this should not be allowed. So under no consistency model we ever allowed such a thing to happen, but that's for the same address. This one says different addresses. So it doesn't matter this is address 1 or that's address 100. This says that this load should finish before this load. Okay, so understand the difference. Yeah. They can be mutually exclusive. So these are 4 different things. Sequential consistency enforce all of them, but yes, we can have, for example, we can enforce the first one and second one, but not the third one and fourth one. They don't. They are mutually exclusive, but the hardware can enforce one or the other or all of them. Did I answer your question? Okay. So they can be independent. I think that's what you're asking. That enforcement of this could be independent. That is, I can enforce the fourth one, but I don't necessarily need to enforce the third one. Okay? The whole thing about the memory model is that the programmer needs to know which one of these you're enforcing, so that when I write my program, I write it based on this. So if you tell me that writes can, like this one is not being enforced, that is, writes can be reordered, then I need to write my program such that if the writes are reordered, it still produce the right results. Okay? So that's very important. Any other questions? Great. Okay, so as I said, sequential consistency enforce all of this. It's great. It's used to be used in some simple systems. In all the modern systems, we don't use sequential consistency. What we do instead is we really want to be reorder something, right? So maybe we can reorder reads before writes. Maybe we can reorder some of the reads before some other reads. We want to be able to reorder some of the things, okay? So this will result in what we call a weak here, or a relaxed memory model. So when you heard the term weak memory model, it means that it's not sequential consistency. So sequential consistency is the strong memory model. It's the strongest possible because it enforces all the possible for reordering. Weak or relaxed memory model means that it doesn't enforce all 4, or sometimes it enforces some of them, or sometimes it doesn't. So there is a little bit of wiggle room in terms of what can be reordered. The specifics of the weak model is based on the ISA usually. So for RISC-V, we're going to talk about RISC-V weak memory order, which I'm going to talk about in the next few slides. But generally what it means, if you heard the term relaxed or weak, it means that there are some possibility of reordering. Which one can be reordered? We don't know. You have to go specifically and read about the details of that memory model. For ARM, it's slightly different than x86. It's slightly different than RISC-V. Okay, so just keep that in mind. Okay, so as I said, some of these reorderings becomes possible under a weak or a relaxed memory model. Okay, so I'm going to talk about, I think, 3 different relaxed memory models. I'm going to talk about total store order, or TSO, and this is a very common one because all the x86 machines use TSO, so Intel is using TSO. Then I'm going to talk about RISC-V weak memory model. Maybe I think that's the right acronym for it. And then I'm going to also talk about release memory model, or release consistency. Okay, so what is TSO? TSO basically says that, remember I told you we have store buffers or LSQs, right? If I have store buffers, here's what I can do, is that I can move my own writes in front of my own, I can move my own reads in front of my own writes. So I can basically, if I have a write here and read here, I can issue the reads sooner if I need to, okay? How do I do that? I have the store buffer. I make sure that the stores are synchronized and ordered. But what I can do is that I can make sure that the reads happens before the writes. Okay, this is very, very beneficial because reads are the ones that are latency sensitive. So you want to issue reads as soon as possible. That's why you're kind of incentivized to issue the reads before writes. Okay. But important things about the TSO is that TSO maintains the following important point, that if someone else is reading from the address address, from address I, the others will see the updated value all the time. Okay, so we still maintain this very key component that if a write happens to an address, everybody else will see the updated value. Okay, so TSO ensures that. So even if you're reordering it later, it will ensure that if there is a previous writes, that writes happens first before that read. Okay, that's an important aspect of the TSO. Remember that we also talked about this when we were talking about out order processors, right? So we said that we have a store and we have a load. Sorry, it was like this. So we have a store and we have a load, and we said that we take this load and says that, oh, okay, let's actually issue this load. If it's not dependent on the store, we are good to go. If it's dependent on the store, we redo it. Okay? That's exactly what this says. That it says that I can issue the load, I can move it behind the store, but what will happen is that if this store is indeed from this load, then I'm discard this load and I move it after the store. Okay, so same thing that we discussed before, that TSO, it gives you that capability. Okay, yes. Yes, both of them. Yeah, all of the cores will read the correct value. That's what you guarantee with TSO. Okay? So for example, how does TSO helps here? So imagine that you have a multi-thread program that you have, like, you store 1 to A and you store 1 to flag in thread 1. So A is equal to 1 and then flag is equal to 1. And then in thread 2, you have some form of a loop that basically checks the value of the flag, and once flag becomes 1, then it loads A. Okay? Under TSO, this will guarantee that you always read the value equal to 1. Okay? Why? Because essentially what this says is that stores will happen in order. Okay? And then if the stores happen in order, then this will happen first and this will happen next. Okay, so it's not possible that the flag becomes 1, okay, before A is already 1. So under TSO, we make sure that the write happens in order. Okay, and under this case, I will not execute this instruction before this loop has been this condition has been met. That is, if flag stays 0, I never will execute this, right? This is just a control flow dependency that I'll never violate. So what will happen is that if flag is equal to 1, then it is guaranteed that A is equal to 1. Does that make sense? Because on the other side, we guarantee that the writes happens in order. If we didn't guarantee that the write happens in order, in other words, flag can be written to 1 first, and then A becomes 1, then it would be a possibility that A reads 0. Yeah.
How would it? So you said it's possible that. And what's the
What? Say again?
So you said that if you switch the order,
yeah,
of turn 1 could be 0.
Yes.
What is the possibility?
Yeah, so the possibility would be this, that I have this sequence: store 1 flag, then if flag equal to 0, go to loop, then load A, then store 1 to A. If this is a sequence of instructions that's being executed, then load would be equal to 0. Do you agree? So flag is first written to 1. That means that this condition is no longer met which means that we're not going to go back to the loop. We're going to exit the loop. So we're going to execute this instruction. At this point, A is still 0. Initial value of A was 0.
Oh,
So we read 0 here, right? So it says that the initial value is 0. And then the store is happening. So this is a race condition, right? So now there is a race condition between these two guys. Whoever happens first, that's the value you're going to read. So that's you don't want this to happen. And why this happened? Because here we relax the right ordering. TSO helps you with that it doesn't relax the right ordering. But if I have a weaker model that allows the right reordering, then this will be messed up. You had a question?
just want to double check that TSO, like, you sure the stores.
Stores are in order. The only things that allows is read before writes that can happen. But again, someone might ask that, oh, why this read? So why this read doesn't happen before this? And as I said, this is usually we do control. So consistency doesn't mean that you don't follow the reordering. Okay, it doesn't follow the program order. You still have your program order. That means that if you have instructions within the for loop, those happens before things that happens outside the for loop. You cannot move things around. Okay, so just keep that in mind that we always enforce the control flow program ordering in a single core. So within each core, you still apply all those rules that you had in the past. It's not like you magically now load A before flag 0 or things like that. Okay. So it's still like things happens retire in order. So you have the branch and you retire in order. Things still happen in order. Just keep that in mind. Okay. All right. So there are a bunch of different weak consistency models. So actually, if you look at the different books or like search Wikipedia or search online, you will see that there are multiple different weak models. And as I said, different ISAs have different weak models. The difference between them is what can or cannot be done when the memory access can be issued. But ultimately boils down to these 4 possible reordering, right? So just keep that in mind that essentially what each of these weak memory consistency models tells you is that what is possible and what is not possible. The trade-offs is between the performance and the complexity. So the least amount of enforcement gives you the highest performance. So if I can reorder everything, that's the maximum performance I can get. But if I can reorder everything, then it's almost impossible to write a correct program. So you have to also think about that complexity of writing a correct program when you can reorder many things significantly higher than when you don't. But on the other hand, you also want to be able to reorder. So you understand the differences. Okay? The one that I want to focus a little bit more is the RISC-V model. So as I said, RISC-V use RISC-V weak memory order. And this is a weak model. It's some sort of a TSO, but it's weaker than TSO. Okay. So what it does is the following. And then, as I said, this is the boom core is the out of order version of RISC-V that's actually implementing this. You can search through the documentation of a boom core. That if you remember, I showed you the block diagram of a boom core when we were talking about the out of order. So it actually implements this this model. So what does it do exactly? So it does the following. So loads are fired to memory once they arrive to LSU, the LSQs. Okay. So essentially, when we push things into the load store queues, we issue them to the main memory. So we read it from the main memory opportunistically. Okay. What it does, though, is that, as we said again in the class, that it compares its address with the stores that depends on it. If it sees that there is a store before, the older store, then the memory request will be killed because the store needs to happen first, and then the load has to happen, right? another thing is that if the store value is already present, instead of killing, we forward it, right? So there's no need to kill the request if I already have the value, store value inside the LS. So we actually do what we call the store to load forwarding. Okay, so we provide the value that you want to store directly to the load so that the load can continue. Okay, and then again, if the store value is not present and it's in fact is dependent, we kill and we let the load to stay in the LSU. In other words, we let it to sleep until the store value becomes available. Okay, so if I have a store and I have a load, right? So what will happen that this load should get its value from the store, right? So what this one says is that as the moment that the store comes to the LSU, we fire it, okay? If there is no other addresses that are dependent here, we let this to continue and then we get performance boost. If we find a previous store that is dependent, we're going to kill this request because it's no longer a valid request, right? Because there is an updated value that needs to happen first. Then the second thing that we're going to do is that we're going to see if the value is actually available here. If it is available, we're going to forward it to this load, okay? And load can continue. It doesn't need to go to the main memory. I have the address for you in the LSQ. You give that to the address. If the address is not available, because, for example, this address itself is dependent to some previous instruction, this load has to stay. It cannot be issued. So we put it into sleep. It waits for all the previous stores to be finished. Then we provide the value and the load continues. So this basically means that you have to stall the processor if need be. Okay? Any questions here? That's we already covered this when we were talking about the LSQs and ADL order. So that's kind of the idea. Okay? So essentially what this means is that the write-read constraint is relaxed, right? So read can happen before writes, right? Read constraint is maintained. So loads the store in the same order. And that's kind of like what we're doing for the weak model here in RISC-V. Okay, so essentially, as I said, it's like similar to the TSO. What it does is essentially making sure that the read can happen before stores, but if it's a dependency, we'll kill that read. Questions? Great. All right, so that's it with the memory model. As I said, there are a bunch of other memory models that we're not going to go through. There's actually one called release consistency that we're going to talk about once we talked about the primitives. But just keep that in mind that there exists these kind of different memory models. MIPS and ARM memory model is slightly different. There is also like I think some read that can be reordered if I remember correctly. But if you're interested, just take a look at them as well. Okay. All right. So last thing I want to talk about, I don't think we're going to be able to finish it, but we're going to cover most of it, and then the rest of it will be Thursday. Would be on synchronization primitives. So first, we're going to talk about a little bit about these primitives, but mostly we're going to focus from the hardware side. For those of you who've taken operating system course 111, you probably have seen these synchronizations before. You've seen like mutexes and semaphores and all that. How many of you are familiar with like what is a lock and semaphore? Okay, a few of you. All right. So we're gonna like give you some broad description of that, but mostly we're gonna focus on what an ISA like RISC-V ISA provides to implement this primitives. Okay. So how do we write a correct multi-thread program? We take the memory model. So for example, say that you want to write a parallel program for a RISC-V. Now you understand what is possible and what is not possible. Now what you need to do is that you need to use these primitives to make sure that the system works correctly. Okay? First thing that you can do when you're writing a multi-thread program is write it such that it's completely race-free. Okay? So being race-free is one way of fixing this problem. It's incredibly difficult. In most cases, almost impossible to make it race-free. Okay? The second thing that you can also do is put everything, like every check in the hardware, and let the hardware basically decide what should happen first and what should happen next. This is also almost impossible, although it's feasible in some cases. So it could be consistency problems and race condition problems solved in hardware. But that means that now I need to understand the context of the program. I need to understand the timing and all that. Again, it becomes very, very costly for the hardware to do it, okay? So what we do instead is using synchronization, okay? So the programmer use this kind of, think about this as some form of an API or instructions, and use them in order to make sure that the system is synchronized. What are the two ways to synchronize for those of you who know synchronization? What are the two major methods for synchronization? Yes. Locks, but what are the two strategies? So before locks, yeah, locks is what? Yeah. Yeah, so there's a mutual exclusiveness that you can do. That's one way of doing synchronization. What is the second one? Come on. How many of you? Yeah. Say it again. Say it out. Monitors. Can you define further what you mean by monitors? Well, that monitors is also similar to mutual exclusiveness in some sense, right? Are you talking about monitors implemented in all OS? Yeah. Okay. So the simpler way is what we call a producer-consumer model. So probably you've heard about barriers, right? Semaphores, barriers. So what we do is the following, is that we let one to produce, we let the other one to consume, okay? So we always like have these kind of like barriers and say, okay, you go up to this point, and then you go to this point, and then you go to this point. So it's kind of like, you do this like one after another kind of behavior, okay? That's one way of doing this. And the second way is, as you guys said, that you do a mutual exclusiveness. That is, if it is a shared resource, so for example, it's the same address or the same variable, you let each one to do that. There is no specific kind of ordering. So either one or two can go, but you make sure that only one of them can use that and read that. So we don't let one or the other do it at the same time. You provide some mutual exclusiveness to achieve this. So these are the two common ways to achieve synchronization, okay? So let's actually talk about this kind of model. The producer-consumer model is typically one of the key things that we use to enforce that is using fence, okay? So what is a fence? Fence is literally an instruction. So RISC-V actually do have a fence instruction. What does fence do is it serializes all the memory reads and writes from that instruction. So for example, you have a bunch of stores and loads, and then you have a fence. So you have a bunch of loads and stores, and then you have the fence instruction. And then you have a bunch of other loads and stores, okay? So what will happen is that the fence instruction, particularly this fence I instruction in RISC-V, what it says is that I don't care what happens here, prior to the fence. You can do whatever reordering based on your memory model. I don't care. Do whatever you want to do. Also, you can do whatever reordering here. But what this says is that at this point, all the reads and writes should be finished before these guys can continue. Okay, so this what fence does is that it serializes all the reads and writes up to that point. So at this point, I know everything before me is finished. Okay, so fence is very, very handy in many cases, because if I only care about at this point everything has been written, then I can put a fence and then move forward with that. Okay. So the actual opcode for a fence is like this. So there is an actual opcode. There is an RD, which is 0 because there's no destination register. There is no source register. The func3 is actually a value that is for fence, and everything else is really zero. So you can actually have an instruction like this inside your ISA for RISC-V that does this for you. How do you implement this? There is the simple implementation is that when I see a fence, I basically flush everything. Okay, so I flush my cache, I flush my pipeline, I flush all of the states, all the levels of cache. So if I do that, I ensure that everything is done, right? So there's no copy, there's nothing else. A more complex one is that you can do it by some form of a snooping. So you can snoop the data and you make sure that if there is any access before that, you don't let the access to happen and so on and so forth. So there's actually quite involved implementation of a fence instruction. It's very complex instruction. That's why actually many a simple processor does not support a fence, but many high-end processors that actually do implement a fence. The second thing about fence is that fence is terrible for your performance because essentially it means that things are flushed. So after you run the fence, you kind of start from, if you're flushing everything from your cache and all, you start from kind of like an empty cache. So there will be lots of misses as a result of running a fence. So just be careful about that as well. But as I said, sometimes you really do need to have fences. So that's also something to keep in mind. RISC-V also added more flexibility. So instead of having a fence I instruction, it also has this other fence instruction. For example, it has this instruction, fence instruction, which is fence RR or fence WR and so on and so forth. So in fact, this is the opcode for it. So it has 4 options, R, W, I, and O. R means read, W means write, I means inputs, the IO inputs, and O means IO outputs. So what this says is that depending on what you put here and what you put here, you can synchronize and serialize only those. So for example, fence RR means that if I put a fence RR, it means that all the loads before this should happen before all the loads here. So I don't care about stores. The stores can happen here, but I cannot have a load here that happens after the fence. So fence RR means that I only care about making sure that reads are serialized. Fence WR means that I care about stores to be finished before all the subsequent reads. I can have something like fence RWR, which means that all the reads and writes should be finished before a new read can happen. I can have a fence RWRW, which means that this is essentially the original fence, that all the read and writes happens before all the next read and writes, okay? How do you encode this? This is how you encode it, okay? So essentially in opcode, so you put your opcode, RD is 0, this is for fence, this is 0. This is S, so these are all this second part. So for example, if I want to do this instruction, sorry, if I want to put this instruction, oh, it decides to update itself. Okay. All right. Yeah, okay. So if I want to do this instruction, what I would do is that I put a 1 here and a 1 here, and I also put a 1 here and a 1 here. This means that I'll do fence RW. Okay? And then if I want to also add the input and output, I can also do II. So that means that fence RWI, IO, fence RWIO means that all the read and writes and all the IO inputs and outputs should be finished before all the inputs and outputs and all the read and writes. Does that make sense? Great. Okay. I guess I'm going to stop here. After this, I'm going to talk about how do we implement locks. And then on Thursday, we also, once we finish the remaining of these slides, we're just going to have a overview of review of all the things and kind of a little bit of what are the steps after this in a more advanced computer architecture and so on. Module 13 will be part of your quiz, but then everything else that we will be on the module 14 won't be part of your quiz. Okay? Thank you.